Okay guys, PowerPoint 20, last one of the unit, hang in there, we're nearing the end. So for this one we're going to be evaluating acid-base disturbances, which is a fancy way of saying we're going to be looking at arterial blood gases. So a little background on arterial blood gases. This is a common diagnostic lab that respiratory therapists will draw. The blood that we're drawing is coming from the radial artery in the wrist, or it can come from the brachial artery in the arm. You don't really have to worry about that anatomy yet. The important takeaway is that we're drawing arterial blood. A lot of the times that you go to donate blood, donate plasma, get labs drawn, they're drawing from your vein. Venous blood is the blood that's going to your heart from your body. We're drawing blood from the artery, which is the blood that's leaving the heart going out to the body. And what we're looking at in order is pH, PaCO2, which is the pressure of CO2 in your arterial blood, PaO2, which is the pressure of oxygen in your arterial blood, and then we're looking at something called bicarbonate. Now, this tells us a ton of information about disease process, how to treat a patient, interventions that we should be doing, changes that we should be making. It's a big diagnostic test that we do very, very frequently. You guys will see them in clinical quite often. I want to soapbox for a minute and give you a little bit of a lecture, and then I will continue on. When you're talking about blood gases, and I'm just going to be transparent, if you go on the internet, there's a lot of ways to cheat at blood gases. You can use shortcuts. There's a lot of things where you can just plug in the blood gas and it will tell you what it is. And I'm going to challenge you early on not to do that. Blood gases are tricky in the beginning, but if you practice them, and I will give you plenty of practice, and you really dig into what each component of the blood gas means, and you understand them conceptually, it is going to make you a way stronger respiratory therapist. And I'll give you an example of how that happens in the clinic. So if I draw a blood gas on a patient and those results come back abnormal, it is my responsibility to directly report that to the physician. Now, I might be working with a first-year resident who's not a pulmonologist, whose expertise is not at all in the intensive care or in pulmonary, and they are going to rely on me to interpret that blood gas for them. And it's not that there's nothing wrong with them not knowing that. Physicians have all kinds of specialties. They go through a lot of schooling. They learn a lot of information. And so that's why we have respiratory therapists, so we can be the expert in a smaller component of the body and really drive healthcare, drive patient care, and be the kind of interpreter of some of that information. So if you understand what an abnormal blood gas means and can recommend an intervention appropriately, that doctor, that physician is going to trust you. And it just, for me personally, I really enjoy that. I enjoy being able to make recommendations, be trusted by other staff, and be a real collaborative colleague versus just somebody who can push buttons. The other thing too is it's going to be really embarrassing if you're sitting next to a physician and you pull up abnormal lab results and you have to Google what that blood gas means because you never properly learned it. So that's my soapbox moment. Take the time. It's not that bad. We're going to have lots of practice, and you can do it. You can learn it. So this first slide is just going through the normal ranges for all the data that's included in a blood gas. So it's always reported in the same order. So you're going to start with your pH. That's always going to be the first number that you see. The normal range for pH is 7.35 to 7.45. We talked about pH with our oxyhemoglobin dissociation curve, so we're going to kind of really hone in on pH with this as well. The next number that you're going to look at is your pressure of arterial carbon dioxide, and the normal values for that are 35 to 45. For your pressure of arterial oxygen, 80 to 100 is your normal. For your bicarbonate, which is HCO3 minus, your normal is 22 to 26 milliequivalents per liter. You don't really have to dig into that unit too much. I'm not going to examine you on that unit. I just wanted to say it so that you know. That's the units associated with it, but that 22 to 26 is the range that we're talking about. On a blood gas, you will also see an SaO2. Normal for that is 95% to 100. You will see a hemoglobin number. That's going to usually be 15, and that's grams per deciliter. Below that, you're going to see a base axis, which we don't talk a ton about. It is relevant, but it's not the biggest component, so that's why I made it not bold and a little bit smaller. And then we're going to talk about an anion gap. Again, not a huge component of what we're going to be talking about or our overall interpretation of a blood gas, which is why they're smaller at the bottom there. So pH is going to be a measure of acidity or alkalinity of the blood. PaCO2, this is going to be the indication of your respiratory status. Think of CO2 as the acid of a blood gas. It's going to make more sense when we start to do our breakdown here, but CO2 is the acid of the blood gas. Just that's the link that I want to make in your mind. For your partial pressure of oxygen, that is going to indicate whether or not you have hypoxemia, and that's going to be your no hypoxemia, mild hypoxemia, moderate, or severe hypoxemia. We gave you those number ranges in PowerPoint 17, so that's what we're talking about here. Your bicarbonate, which is produced by your kidneys, is an indication of your metabolic status. So your CO2 is an indication of your respiratory status. Your bicarbonate is an indication of your metabolic status. Think of bicarbonate as the base for an ABG, and this will make more sense later. So that's the base of the ABG. Your SaO2 is the percent of hemoglobin filled with oxygen, which you guys know, and then hemoglobin is the amount of hemoglobin. So the other things that were very, very small that we're not going to focus on a ton is base excess or base deficit is looking at metabolic processes that are not compensated at all by ventilation. So for your guys' life, what you have to know is the normal is plus and minus 2 for base excess or base deficit. And then just know that it's either a metabolic alkalosis or a metabolic acidosis, and it's not compensated for. So I'll kind of explain it when we do our interpretation a little bit more, but that's all you really need to know on a flashcard. Your anion gap is this very complicated equation that is your sodium minus chloride minus bicarb together, and it's basically the balance between your positive anions and your negative anions, and it should be between 18 and 16. This has a lot to do with like electrolyte values and electrolyte balances. We're going to talk a little bit more about this when we get into neurocontrol, but this is not something that you would really talk about in your normal interpretation of a blood gas. So for this unit, I want you, just so that you guys don't have one more thing, you can kind of cross this off in your mind. I am not going to examine you on the anion gap, so you can just put a little extra this in your brain. We might circle back to it later in Unit 4. But for right now, I don't want you guys to waste your brain space on this. So that's not an important part of this for right now. Okay, so this is the most complicated version of it, but this is the math associated with balancing the acid base of a blood gas. I'm going to go really quickly through this. This is the Henderson Hasselbach equation. You're never going to put this equation or plug in this equation to anything, but this is how the acid base or pH of a blood gas gets determined. To simplify it, pH basically equals kidney or bicarb over lung or PCO2. So there's a balance between base and acid. And there's a mathematical way to view it, which is that Henderson-Hasselbach equation. But we're going to just talk about conceptually. Conceptually speaking, in your body, you constantly have this balancing act between your kidneys producing bicarb and your lungs getting rid of CO2, and they are going to kind of equalize or balance to create a normal pH. And a normal pH is 7.35 to 7.45. If this gets bigger, this gets smaller, things go out of whack, you're going to see that reflected in your pH. And I will show you that in our blood gas interpretations. So really quickly to talk about pH, this is our normal range. If you get higher than 7.45, it means that you're getting to be alkalotic. Alkalotic is another way of saying you're getting to be more basic. You have a higher base. So an alkalosis means you have a higher base. We talked about how in the blood gas, the bicarb is the base. Over here, if you're less than 7.35, you're now getting into acidotic territory. Your blood is getting more acidic. That is going to be your CO2. So the CO2 is the acid of your blood gas. And you're going to see how this kind of works when we get the numbers. But some people aren't aware of like what an alkalosis means or an acidosis means. So alkalosis is basic. It's higher than 7.45. An acidosis is the acid, and it's lower than 7.35. So that's just the scale of pH. So just to show you kind of some of the things that can happen, and you're going to see a ton of blood gases in your clinical rotation, but 7.40 would be perfectly normal because it's the dead middle point between 7.35 and 7.45. When you start to drift down into an acidotic state, you get drowsiness, you start to get very lethargic, fall asleep, you go into a coma, and then you can die. From the alkalotic side, when you get basic, when you have a high base, you get irritable, you start to have cardiac arrhythmias, seizures, and then you die. So these show you what they consider to be the top ends or low end here. You will be amazed how much you will see this vary in a patient population where they are able to compensate for some pretty gnarly pHs. But the goal is obviously to try to stay at the 7.40. Okay, so when you're interpreting a blood gas, your first step is it acidotic, is it alkalotic, or is it normal? So this is a refresher of the normal range is 7.35 to 7.45. So that would be normal. If your pH is greater than 7.45, you would consider that to be an alkalotic pH. If your pH is less than 7.35, you are going to consider that an acidotic pH. So this is your first step, normal, alkalotic, acidotic. Your second step is to figure out, is this a respiratory issue or is this a metabolic issue? So the PaCO2 is your respiratory side. The bicarb, or HCO3- is your metabolic side. So what is the driving force for the abnormal pH? So if you have an acidic pH, which is that less than 7.35, it can either be caused, by a high CO2 or a high acid, or it can be caused by a low bicarb or a low base. So high CO2 equals high H+ ions equals high acid, okay? All of those things essentially the same. Think back to the oxygen dissociation curve where it said high CO2, high H+ ions, right? High acid. So high CO2, high H+ ions, high acid. If you have a high acid, that is going to create a low pH or an acidic pH. The other thing that can cause an acidic pH is if you have an abnormally low bicarb. So low bicarb equals low base, which is going to equal a low pH or an acidic pH. So both of those things could happen and create an acidic pH. If you have a basic pH or an alkalotic pH, that can either be caused by a low CO2 or a low acid, or it can be caused by a high bicarb or high base. So low CO2 equals low H+ ions equals low acid. This is going to create a high pH or an alkalotic pH. The other scenario could be that you have high bicarb or a high base, which will make a high pH or an alkalotic pH. You can also have a situation where your respiratory and metabolic are working together, essentially, to make a mixed or combined. So basically, it could be a situation where both are the problem, and we'll talk about that as we move through this because I think it's kind of hard to understand right now. So, is it a respiratory issue or metabolic issue? Here are some acidosis examples for you guys. So I am starting off with a normal blood gas. So 7.40, normal. 35 is a normal value for your CO2. 85 is a normal value for your PaO2. 24 is a normal value for your bicarb. Coming down to this one, right away, I see that this is an acidotic pH. And the reason I know it's acidotic is because it's less than 7.35. Well, my CO2 is normal, right? That's not abnormal, so that's not the issue. I go here, my oxygen is normal. Over here, my bicarb is 12. That is lower than the normal range of 22 to 26. I also know that the bicarb is the base of my blood gas. It's the basic side. So if I have a low base, it's going to make an acidotic pH because I don't have enough base. So this is a metabolic issue caused by the kidneys. So this would be considered a metabolic acidosis. You have a bicarb that's lower than the normal range. What's going to help you guys too is as you memorize the normal ranges, it's easier to identify which is the abnormal value. Down here, I have the same pH, 7.20. Again, right away, I'm going to identify that as acidotic because it's less than 7.35. But here, I don't have a normal CO2. I have a CO2 of 68, which is very high. So that's a high acid. I have a normal oxygen, and then I have a normal bicarb. So my base is normal. The alkaline side of this blood gas is totally normal. So what is causing this blood gas to be acidotic is this high acid right here. CO2 is the acid and it's elevated. So this is a respiratory issue. This is the lungs. This would be considered a respiratory acidosis. The CO2 is higher than the normal range. Hang in there, guys. This is one of those things where repetition and practice is how we start to understand it. Just keep repeating, keep practicing lots of examples, and I have those for you. And we're going to do a bunch of examples in class. So just hang in there. Okay, so now I have examples of an alkalosis. Okay, we just did an acidosis. Now we're going to do an alkalosis. So again, starting with the normal blood gas, you have 7.40, which is in the normal range of 7.35 to 7.45. Normal CO2, normal oxygen, normal bicarb. There are no abnormal values, so it's a normal blood gas. You come down here, and the first thing that you notice is this pH is not normal. And it's alkalotic because it's above 7.45. So this is a high pH, it's alkalotic. When I go to this next value, well, that's in the normal range. You have a normal amount of acid. You're at 35. You come here, you have a normal oxygen. Now you come here and you have a high bicarb. The normal range for bicarb is 22 to 26. Here, this patient has a bicarb of 42. That's higher than normal range. It's a high base. And because you have a higher amount of base, you're going to drive a more basic pH or an alkalotic pH. It's a metabolic issue caused by the kidneys because the bicarb is the abnormal value. So you have what's known as a metabolic alkalosis. The bicarb is higher than the normal range. Coming down to this one, same pH, the 7.50 that we've realized is alkalotic because it's higher than 7.45. But now when we come to the CO2, it's no longer normal, it's low. It's lower than the normal range. So that would be considered a low acid. Oxygen's normal, bicarb is normal. So for this one, the reason that you have this high alkalotic pH is because you have low acid. You don't have enough acid. So that is what's driving this. So this is now a respiratory issue, lungs, and it's specifically called a respiratory alkalosis. The CO2 is lower than the normal range. So I also mentioned that they could both be to blame. There is also a possibility where it's called a combined or mixed alkalosis or a combined or mixed acidosis. So again, starting off with your normal blood gas, no abnormal values, normal. Here you have that same alkalotic pH that we talked about before. So this is a high pH, it's a basic pH, it's an alkalotic pH. All means the same thing. You have a low acid. That's an abnormal value. That's lower than 35. You come over here and then, you have an abnormal bicarb. That's higher than 22 to 26. That's 42. So here's an example where you have a low acid and you have a high base. Both are contributing to this alkalotic pH. Low acid, high base, more basic pH, higher pH, alkalotic pH. So this would be a mixed or combined alkalosis. Your CO2 is lower than normal, your bicarb is higher than normal. They're both to blame for this out of balance pH. Down here, this is an abnormal pH as well. This is less than 7.35, so we consider this a low pH, an acidotic pH. When you come to the CO2, you see that that's higher than the normal range of 35 to 45, so that means you have a high acid. We're ignoring the oxygen for right now. Here we go to bicarb, and you have a low bicarb. So you have a low base and a high acid, and you have an acidotic pH, right? So you have this very low pH, very acidotic pH. You have a high acid and a low base. So both are the issue for this pH. So you have a mixed or combined acidosis because you have a CO2 that's higher than normal, high acid, and a bicarb that's lower than the normal range. You have a low base or low basic part of this. So that's why it's an acidic pH. So you're always kind of looking for the balance between your CO2 and your bicarb. The oxygen is something that you guys are going to interpret as well, but that's going to be interpreted just kind of by itself. Oxygenation is kind of its own component. These three, your pH, your CO2, and your bicarb, are that Henderson-Hasselbach equation. You have pH equals bicarb over PaCO2. The balance between bicarb and CO2 is really what's going to determine your pH. So you want to be looking at what is abnormal, what does it mean, and how do they compensate or balance one another. Okay, speaking of compensation, the next step is it compensated or uncompensated? So again, you have your normal blood gas at the top here. There's no abnormal values. Down here, you have a normal pH, right? 7.36, normal pH. It's between the range of 7.35 and 7.45. But when you come over here, that's not normal. And that's not normal. So how do two abnormal values make a normal pH, right? It doesn't seem like that should work that way. In all the other examples, if we've had an abnormal value, we've had an abnormal pH. So why is this different? And the reason that this is different is because these numbers are working to balance each other. So you have to see which one is the problem and which one is the solution, or which one is potentially compensating. Because your body is always going to look to right the wrongs of a disease process. It has millions of ways that it compensates for the things that we do. This, with your blood gases, your body wants to maintain a normal pH. You know, we saw the scary chart. If it gets too far off normal, you die, right? Or have pretty bad symptoms. So your body is always trying to maintain this normal pH. So it's our job to figure out how it's doing that. So here you have a normal pH, but you have an abnormal CO2 and an abnormal bicarb. So if you're looking at this normal pH, it's 7.36. That's very close to the acidotic side of the normal range. So like if you were lower than 7.35, you are considered acidotic. Here you have a high acid and you have a high base. So this would be considered a fully compensated blood gas, because even though this is abnormal and this is abnormal, they have balanced out and created a normal pH despite being abnormal. The reason that you know that the problem is the CO2 is because even though this is normal, it's on the acidotic side of normal. So if you think about 7.40 being the dead middle of that range, so from 7.35 to 7.4 would be considered like the acid side of normal. And from 7.4 to 7.45, that would be like the alkalotic side of normal. So this is on the acidotic side of normal, and you have a high acid. So I know that this is the problem. And then your bicarb, your kidneys have produced more bicarb to compensate for this problem here. So this is a fully compensated respiratory acidosis. We are going to practice the heck out of this, guys. I swear. I know this is a lot. We will practice it, and you will figure it out. The next one is comparing this fully compensated to an uncompensated. So here you have an acidotic pH, 7.20. you have a CO2 of 68, which is a high acid. We're not going to worry about oxygen for right now. And you have a normal bicarb. So this would be considered an uncompensated respiratory acidosis. So the difference being, here you've got a crappy CO2. Here you've got a crappy CO2. You've got a high acid, high acid. The difference between the two is this one has had some time. The kidneys have produced bicarb, which is basic. They've balanced that acid and they've normalized the pH. For this one, you have this high acid. The kidneys have not compensated. They've not produced more bicarb. And so your pH is significantly worse. It has not normalized. There's no balance there because this high acid is making this acidotic. So that's what we're talking about when we're talking about compensation. I got a little click happy. Sorry about that. That's what we're talking about when we're talking about compensation. Your CO2 and your bicarb are always kind of trying to balance. So one is always going to be the problem and one is always going to be the solution. And we call the solution the compensation. So either it's going to fully compensate, it's going to partially compensate, or it's going to be uncompensated, which means it's not going to do anything. So this is a circumstance where you have this very abnormal CO2. The bicarb has not done anything. Here you have this abnormal CO2. It's the problem. You know it's the problem because it's a high acid, and this is on the acidotic side of normal. And your bicarb is trying to compensate. Your kidneys have produced more bicarb. It's trying to compensate, and it's able to give you a normal pH. So I'm going to show you a comparison of uncompensated, partially compensated, and fully compensated. And what I did here is I tried to use all of the same numbers so it's an easy relation. You're not going to worry about the oxygen at this point. So 7.20, acidotic pH, less than 7.35. You have an abnormal CO2. That's your acid. Abnormal CO2, it's elevated. Not going to worry about oxygen, and your bicarb is normal. So this would be considered an uncompensated, because the bicarb is normal, it hasn't done anything to help, uncompensated respiratory acidosis. It's an acidosis because the pH is low. It's respiratory because the CO2 is the problem, okay? And it's uncompensated because the bicarb has done nothing to compensate. So uncompensated respiratory acidosis. Here you have the same pH, the 7.20, which we know is acidotic. You have a CO2 of 60. We know that that's the high acid. We know that that's probably what's driving it. And you have a bicarb of 30, which is higher than the normal range of 22 to 26. So this is considered a partially compensated respiratory acidosis, and this is why. Your pH is acidotic. It's not at all compensated for. Like it's still abnormal. Your CO2 is high. You have a high acid. Your bicarb is trying to balance it out, but it hasn't been successful. So it's a partially compensated. It's trying to compensate. It just hasn't done it yet. So this is increasing. Your kidneys are producing more and retaining more bicarb, which is the base of this whole equation, to try to neutralize this acid, which is happening here because of hypoventilation. Your CO2 is high, and that is causing in turn an acidotic pH. Okay, down here we have a normal pH, and I don't know why I made that 7.40. That should be 7.39 or something lower than 7.40. Because right when it's in the middle, it's pretty impossible to figure out which way it goes. My bad. So let's imagine that that's less than 7.40. You have a high acid again, and then you also have a high bicarb again. So your acid is the problem. The high CO2 is still going to be the problem. And your bicarb has been retained enough by your kidneys that it has fully compensated. It has balanced out, and you now have a normal pH, okay? So just for future reference, if you ever have a fully compensated blood gas, you will not have 7.40 for a pH because it would be impossible to determine which one was the problem and which one was the compensation. So that was just an oversight on my part. Shocking, I know. So that's the way that the uncompensated, partially compensated, and fully compensated work. So this kind of takes you through what we just did in another way. So you have your pH is at normal, no abnormality mixed or is it compensated? Over here, if your pH is low, you have an acidemia. Do you have a high PCO2? Then it's a respiratory acidosis. If you have a low bicarb, it's a metabolic acidosis. And then just kind of following this through. I don't know if this is super helpful for me. I don't really like these decision tree ones, but it's just a diagram going through the decision process that we just talked through. pH, if it's low, it's an acidosis. 7.35 to 7.45 is normal. If it's higher than 7.45, it's alkalosis. Respiratory PaCO2, if you have a high PaCO2, you have a high acid, so acidosis. The normal is 35 to 45. If you have a low PaCO2, then you have an alkalosis because you have a low acid. For the metabolic bicarb, if you have low bicarb because it's the base, you are going to have an acidosis. The normal is 22 to 26. If you have high bicarb or a high base, you're going to have an alkalosis. Same information, different way to check it out there. This is just a reminder of the hypoxemia. That 80 to 100 is no hypoxemia. 60 to 79 is mild hypoxemia. 79 to 60. 59 to 40 is moderate hypoxemia, and less than 40 is severe. You also can have that hyperoxemia when you're on supplemental oxygen. You can have a PaO2 of greater than 100, and that would be an indication that we want to titrate that oxygen down. You would never have hyperoxemia on room air. This only happens when somebody is on supplemental oxygen. So that's how we classify the oxygenation portion of the blood gas, which we'll talk about in our full interpretation here. So when you add in the O2, because we've been up until this point disregarding it, this is how it goes. So if you're looking at that first blood gas, 7.20, 60, 85, 24, this is an example of an uncompensated respiratory acidosis with no hypoxemia on room air. The reason it's uncompensated is because you have this high acid, you have a high CO2, it's giving you an acidotic pH, and the bicarb is normal. The bicarb is not compensating at all, so it's uncompensated. The reason you have no hypoxemia is because 85 is within the range of 80 to 100, so this patient does not have hypoxemia. And then you always say on room air because it's important to include what they are on for an FiO2. So when you're writing out your full interpretation of a blood gas, it would be an uncompensated or compensated, or so you would have uncompensated, partially compensated, fully compensated. That's the first part. So that's the first part of your interpretation. The next part is it respiratory or metabolic? Next part is it acidosis or alkalosis? And then it's the oxygenation part. So you always write them the same way in the same order. So the next one is an example of a partially compensated one. So you have the 7.20, you have your CO2 of 60, your PaO2 of 40, and your bicarb of 30. So this is a partially compensated respiratory acidosis with moderate hypoxemia on 40%. So it's partially compensated because here you have that acidic pH, you have that high acid, the kidneys have retained and are producing more bicarb to try to compensate for this high acid because this is the base and this is the acid. They have not been able to successfully balance out the pH, so it's partially compensated. This is the problem, so it's a partially compensated respiratory acidosis. Moderate, because that's in the range of 40 to 59 is moderate. Hypoxemia on 40%, and that's what they're on for an FiO2. This one is going to be your fully compensated. Again, you would never have 7.40. That was an oversight on my part, so let's imagine that it's 7.39. But it's fully compensated because here you have this high acid that's been causing the problem. Your kidneys have retained or produced enough bicarb that they have fully compensated for this high acid. They've created enough base to neutralize this acid, to normalize this pH. So it's a fully compensated respiratory acidosis because this is the problem. with severe hypoxemia on 50%. And it's severe because this is in the range of less than 40. So that's how your interpretation reads. And I feel like with these, just practice really helps to drive these home. And then start by memorizing your normal ranges. That also helps. So your 4 steps of interpretation are uncompensated, partially compensated, fully compensated or mixed or combined, acidosis or alkalosis, respiratory or metabolic, and then classifying your hypoxemia and FiO2 as normal, mild, moderate, or severe, or you could have hyperoxemia as well. These are your lecture questions. Go through them. I feel like this one is one of the more intimidating PowerPoints, so I swear we're going to go over it in class, in person. We'll just do lots and lots of repetition where I keep throwing out more and more examples of blood gases, and you guys get a chance to really kind of hone in on where the interpretation is coming from, what's abnormal and why. So repetition for this is really the key, and then hopefully obviously no typos.